Welcome to Calculus Lesson 1. In order to start an exploration into the science that is calculus, we need to get acquainted or reacquainted with real numbers. The symbol used to denote real numbers is a bold R. You may have seen something like this before. Real numbers include all the natural counting numbers like 1, 2, 3, 4, etc. Integers, numbers like -1, -2, -3, and so on. Rational numbers, numbers written as fractions. Irrational numbers, numbers which cannot be written as fractions, like e or pi. If we were to make the real numbers line up in order, we could get a real number line. Real numbers have certain properties: algebraic properties, order properties, and completeness properties. Let's go over each quickly. Algebraic properties. There are commutative properties like a plus b equals b plus a. If you put numbers there, you could say 1 plus 2 is equal to 2 plus 1. The same is true for multiplication. A times b is the same as b times a. There are associative properties where the a and b in the brackets get added first and then added to c, which is the same as having the b plus c added together first and then adding a. And the same is true with multiplication. Associative properties work when the operator is the same, plus, 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 times, 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 times. The distributive property results when you have two different kinds of operators, such that you have the times and the plus, as a times b plus c, where you have to plus the b and c together first, then multiply a, is the same as having a times b plus a times c. Or you can have the a plus b first, times c, which gets you a times c plus b times c. There is the reciprocal property, where you have a times 1 over a will get you 1, as the a's cancel. There's the additive inverse, which is a plus negative a to get you 0. The additive identity, a plus 0, gets you a, and the multiplicative identity, a times 1, is just a. Order properties. For example, if a, b, c are real numbers, then when a is less than b, this implies that a plus c is going to be less than b plus c. If a is less than b, this implies that a minus c is less than b minus c. If a is less than b and c is greater than 0, then this would imply that a times c is less than b times c. If a is less than b and c is less than 0, then this would imply that a times c is greater than b times c, as negative a is going to be greater than negative b. If a is greater than 0, then this would imply that 1 over a is also greater than 0. If a is greater than 0 but less than b, this would imply that 1 over b is less than 1 over a. Completeness property. There are no gaps in the real number line. There exists a real number at any point of it. This leads us into talking about intervals. A subset of the line is called an interval if it contains at least two numbers and all the real numbers between those two numbers. One such group of intervals are the enclosed intervals. There are 4 different kinds of enclosed intervals. The first kind is an open interval from a to b, where x is greater than a but less than b. It can be written parentheses a, comma b, end parentheses. The parentheses are used to indicate that it is open. Open in this case meaning that a and b are not included in the set. There are closed intervals from a to b where x is greater than or equal to a, or less than or equal to b. This is written bracket a, comma b, end bracket. The brackets indicating that the a and b can be included in the set. There are half-open intervals from a to b, such that x is less than or equal to a, which is less than b, or bracket a, comma b, end parentheses. And there's half intervals in the other direction from a to b, where x is greater than a, but less than or equal to b, or parentheses a comma b end bracket. There are also infinite intervals. There are three main kinds. There's open intervals, which can go from a to infinity, or from negative infinity to a, but do not include a. There are half-closed intervals, which can go from negative infinity to a, or from a to infinity. This one does include the a. And then there are half-open intervals from negative infinity to infinity. The half-open interval from negative infinity to infinity is usually just considered all real numbers. Let's do an example. Solve the system of inequalities. 3x minus 1 is less than 5x plus 3, which is less than or equal to 2x plus 15. Recall that the abstract interval would look like this. A is less than x, less than or equal to b, and can be written simply as parentheses a comma b end bracket. So the question is, what is a and b in this example? Start by doing 1/2 at a time, such that you have a less than x and x less than or equal to b. Then replace the abstract placeholders with the concretes. Starting with a less than x, we would have 3x minus 1 is less than 5x plus 3. We can use the additive inverse and the first order property to remove minus 3 from both sides of the inequality, which would give us an equation that looks like 3x minus 1 minus 3x is less than 5x plus 3 minus 3x. Rearranging, we get minus 1 plus 3x minus 3x is less than 5x minus 3x plus 3. The 3x's would cancel. That would leave us with minus 1 less than 2x plus 3. So let's get rid of the 3 from both sides. We'd get minus 4 is less than 2x. Using the multiplicative identity, we can remove the 2 from the 2x, leaving us with x greater than negative 2, or negative 2 less than x. On the other side, we have x less than or equal to b. So we would have 5x plus 3 is less than or equal to 2x plus 15. Like how we did on the other side, we can get rid of the 2x from both sides. Rearranging this, we can get 3 plus 5x minus 2x is less than or equal to 2x minus 2x plus 15. This would give us 3 plus 3x is less than or equal to 15. So let's get rid of the 3 from both sides, and we'd get 3x is less than or equal to 12. Divide the 3 up from both sides, and we get x is less than or equal to 4. Putting this back together, we get minus 2 is less than x, which is less than minus 4. Meaning that x could be any number between minus 2, not including minus 2, up to 4, including 4. One way to think about this would be with Venn diagrams. At this point, we need to introduce interval unions, intersections, and absolute values. Take this line and the subsets. Say that we have every number that belongs in the red zone, including the minus 4, the 1, and the 4, but not including the 0. What would be a good way of showing that these are the numbers that we have? First, let's start by introducing a Venn diagram. If you draw the subset of numbers in an interval in circles, we can make these Venn diagrams. In order to draw the Venn diagram, you need one circle per every set. There are 2 different sets here, so we need 2 circles. For the first set, let's start at the left and move right. We have a black dot on minus 4, meaning it is included in the circle. So we have minus 4, and then as we move right, we'd also have minus 3, minus 2, minus 1. We would also have all the rational numbers and irrational numbers that exist between them. I did not draw them for simplicity's sake. This set would not include 0, though, as that is an open interval. In the other set, we would have 1, 2, 3, 4, and all of the rational numbers and irrational numbers that also exist between them, but not shown here. If we were to overlap these 2 circles, we could try to see what they have in common and what they have as differences. In order to do this, we could fill them in with the same color that we're using to fill in the line. If we wanted our subset to be a union of these 2 subsets, then we could unite them with a union, denoted with this U shape. This would give us all the values that are within these subsets, but none of the ones that are outside of them, such that we'd have minus 4, minus 3, minus 2, minus 1, 1, 2, 3, 4, and all of the rational numbers between those. If we wanted to know what they have in common, we could view the intersection, denoted with the union symbol upside down. In this case, we would have nothing, which is denoted with this empty set symbol. If we change the two sets such that there was some overlap, we could see that there's some numbers in between. The absolute value or magnitude of a number is defined by the formula: the absolute value of x is x if x is greater than or equal to 0, or is minus x if x is less than 0. The vertical bars in this symbol are called absolute value bars. Let's go over some various properties of absolute values. The first one is that a negative value inside the bars is the same as a positive value. The second property is that the absolute value of two numbers multiplied is the same as multiplying those two absolute values. The third property states the same is true for division. The fourth property is that the absolute value of a plus or minus b will be less than or equal to the absolute value of a plus the absolute value of b. This is called the triangle inequality. The absolute value of x is equal to d if and only if either x is equal to negative d or x is equal to d. The absolute value of x is less than d if and only if negative d is less than x, which is less than d. The absolute value of x is less than or equal to d if and only if minus d is less than or equal to x, which is less than or equal to d. The absolute value of x is greater than d if and only if either x is less than minus d or x is greater than d. The absolute value of x minus a is equal to d if and only if either x is equal to a minus d or x is equal to a plus d. The absolute value of x minus a is less than d if and only if a minus d is less than x, which is less than a plus d. The absolute value of x minus a is less than or equal to d if and only if a minus d is less than or equal to x, which is less than or equal to a plus d. The absolute value of x minus a is greater than d if and only if either x is less than a minus d or x is greater than a plus d. Let's do some examples. We have 8 questions here, and we're going to start with number 1. 1. 3 times 2 minus x is less than 2 times 3 plus x. The equation starts with 3 times 2 minus x is less than 2 times 3 plus x. We can use the distribution property on both sides, and we'd get 3 times 2 minus 3 times x is less than 2 times 3 plus 2 times x. This would give us 6 minus 3x is less than 6 plus 2x. If we were to remove the 6 from both sides such that we had 6 minus 3x minus 6 is less than 6 plus 2x minus 6. This would give us minus 3x is less than 2x. We can move the 2x to the other side by minusing minus 2 from both sides. We would get minus 5x is less than 0. If we divide both sides by negative 5, we'd find that x is greater than 0. This would mean that x could be any real number from 0, not including 0, all the way to infinity. Question 2. 6x squared minus 5x is less than or equal to minus 1. If we take the minus 1 from the 6x squared minus 5x less than or equal to minus 1 and put it to the other side, we could get 6x squared minus 5x plus 1 is less than or equal to 0. With this, we have something that looks similar to a quadratic equation. That is, a times x squared plus bx plus c equals 0. In order to solve this, we need to do something which is called completing the square. Let's take the abstract quadratic equation as an example. You have a squared plus b squared plus c equals 0. In order to remove the a from the first term, we have to divide it out, such that we'd have x squared plus b divided by a times x plus c divided by a, which is equal to 0. In cases where the c over a doesn't give us a perfect solution for the quadratic equation, we can remove it by minusing it from both sides. This would give us something that looks like x squared plus b over a x equals negative c over a, giving us x terms on one side and constants on the other. If we were to look just at the left-hand side of the equation, we have x squared. X squared can be seen visually by drawing a square, the lengths of which are equal, in this case, are x, such that the length times the height of the square would be x squared. Using this idea, we can see that the next term, b over a times x, would be the same as the length b over a times the height of x. If we were to divide the b over a in half, we could put 1/2 on the side of the x squared and the other half on the bottom of the x squared. This would leave us with a small square patch in the corner, whose dimensions would be b over 2a times b over 2a. b over 2a times b over 2a would give us b squared over 4a squared. We could introduce this into our equation by adding it to both sides of the equation, such that we would get x squared plus b over a squared plus b squared over 4a squared equals negative c over a plus b squared over 4a squared. We could then follow up with basic algebra. Doing two different sets of algebra on both the left-hand and right-hand side, we would get that the x squared plus b over ax plus b squared over 4a squared is equal to negative ca plus b squared over 4a squared. The left-hand side can be simplified by reversing the expansion of the term x plus b over 2a squared. We can times c by 4a in order to get b squared minus 4ac over 4a squared. Taking the square root of both sides, we would get x plus b over 2a is equal to plus or minus the square root of b squared minus 4ac divided by 4a squared. Getting rid of the b over 2a from the left-hand side, we would get x equals b over 2a plus or minus the square root of b squared minus 4ac all over 2a. Since the two terms on the right-hand side have the same denominator, we can put them under the same denominator, such that we would get x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. This shows us that completing the square gives us the solution to the quadratic equation. So let's plug this in and see what we get. The terms a, b, and c would be replaced by 6, minus 5, and 1. Plugging these into the quadratic equation, we would get x equals minus 5 plus or minus the square root of minus 5 squared minus 4 times 6 times 1 all over 2 times 6. This would give us x equals 5 plus or minus the square root of 25 minus 24 all over 12, which simplifies to x equals 5 plus or minus the square root of 1 all over 12. We can split the plus or minus into two equations. We'd get x equals 5 plus 1 over 12 and x equals 5 minus 1 over 12. So on the positive side, we'd get x equals 6 over 12, which is equal to 1/2. On the negative side, we'd get x equals 4 over 12, which is equal to 1/3. Plugging these back in together, we could see that the 6x squared minus 5x plus 1 less than or equal to 0 would give us x minus 1/2 times x minus 1/3 is less than or equal to 0. We're going to have a problem here if we are not careful. So it's concept time. X minus 1/2 times x minus 1/3 is less than or equal to 0. What is going on here? This is the same as a times b is less than or equal to 0. If both a and b are negatives, we'd get minus a times minus b equals positive ab. Positive ab is greater than 0. Therefore, negative a times negative b cannot be less than or equal to 0. Only one can be negative, so which one? So either x is less than or equal to 1/2 and x is greater than or equal to 1/3, or x is less than or equal to 1/3 and x is greater than or equal to 1/2. If we bring in the number line, we can see that 1/3 is less than 1/2 and we cannot change this. So what we should do is draw 6x squared minus 5x less than or equal to minus 1. On the left-hand side, we have 6x squared minus 5x. And on the right-hand side, we have minus 1. So we can draw these as two different lines. The minus 1 is just a horizontal line at minus 1. The 6x squared minus 5x is a parabola. Putting them together, we can see that there is a small part of the parabola that is less than minus 1. Since 6x squared minus 5x is less than minus 1, the numbers we want must be between 1/3 and 1/2. Therefore, we would have bracket 1/3 to 1/2 end bracket. or 1/3 is less than or equal to x, which is less than or equal to 1/2. Three over x minus 1 less than 2 over x plus 1. Recall the reciprocal property, a times 1 over a equals 1. And the order properties a less than b and c less than 0 implies that a times c is greater than b times c. And when a is greater than 0, this would imply that 1 over a is greater than 0, or in the reverse, when a is less than 0, that would imply that 1 over a is less than 0. To simplify, I want to use the reciprocal property to multiply the denominators to both sides so that I can get the simple equation 3 times x plus 1 less than 2 times x minus 1. However, we don't know if x minus 1 and or x plus 1 are positive or negative values. We would have to check the cases when x minus 1 is less than 0 and x plus 1 is less than 0, when x minus 1 is less than 0 and x plus 1 is greater than 0, and when x minus 1 is greater than 0 and x plus 1 is greater than 0. We don't need to check x minus 1 greater than 0 and x plus 1 less than 0, as that is a contradiction. Because this equation is tricky, let's use a sign information chart. But first we need to reorganize the inequality. Starting with what we have, 3 over x minus 1 less than 2 over x plus 1, let's move the 2 over x plus 1 to the other side so that we have 3 over x minus 1 minus 2 over x plus 1, which will all be less than 0. In order to minus fractions, the denominator has to be the same. So let's times the top and the bottom by each other's denominators and get 3 times x plus 1 over x minus 1 times x plus 1 minus 2 times x minus 1 over x minus 1 times x plus 1. All of this is still less than 0. Sharing the denominator, we get 3 times x plus 1 minus 2 times x minus 1 all over x minus 1 times x plus 1, all of which is less than 0. Distributing, we get 3x plus 3 minus 2x plus 2, all over x minus 1 times x plus 1, which is all less than 0. This would leave us with x plus 5 over x minus 1 times x plus 1 less than 0. By looking at this equation, we can see that when x equals minus 1, the fraction is undefined. The same is true when x equals 1, the fraction is undefined. When x equals minus 5, the fraction is 0. So, in order to determine when this fraction is less than 0, we make a sign information chart. In the left-hand column, we put the fraction, first the numerator, then the denominator, then the whole thing. On the top row on the right-hand side, we put the values of x when we know the things are going to change. In this case, minus 5, minus 1, and 1. So starting with the numerator, we have x plus 5. When x is minus 5, we know there is a 0. If x was more negative than minus 5, x plus 5 would become a negative value. If x was greater than minus 5, it would become a positive value. And this would be true all the way to infinity. So on the top row, we can see that the numerator makes a change from negative to positive at the value x equals negative 5. The second column will contain the denominator by itself. In this case, x minus 1 times x plus 1. We know that when x equals negative 1, or when x equals 1, the value will be 0. If the value were something like negative 5, we would get minus 6 times minus 4, which is positive 24. We could see that any value less than minus 1 is a positive value. If x were a number between negative 1 and 1, such as 0, we would get a case like negative 1 times 1, which is a negative 1. And we can see that when x is greater than 1, we would have a positive times a positive, which would be a positive. The last column contains the fraction put back together, and we can use the other columns to do a logical math to see what would happen here. Starting at the most negative and moving positive, we would have negatives divided by a positive, which would get us a negative number. We could have x at minus 5, which would give us a 0. We could have numbers between minus 5 and 1, which would give us a positive, as a positive divided by a positive is a positive. At -1, we would see it would be a positive divided by 0, which is undefined. Between -1 and 1, we would have a positive divided by a negative, which is a negative. At 1, we have a positive divided by 0, which is undefined. And when x is greater than 1, we have a positive divided by a positive, which is a positive. Recall that the purpose of solving this equation is to find values of x which belong to a set which is less than 0. Using the bottom column, we can see negative values when x is less than -5 and when x is between -1 and 1. Therefore, our set will be between -infinity and -5, union -1 and 1, or -infinity is less than x, which is less than -5, and -1 is less than x, which is less than 1. The line graph would look like this. The absolute value of x minus 3 equals 7. From our properties, we know that the absolute value of x equals d if and only if either x equals minus d or x equals positive d. So we have two scenarios, x minus 3 equals 7 or x minus 3 equals -7. On the positive side, x minus 3 equals 7. Getting rid of the 3 from the left-hand side, we get x minus 3 plus 3 equals 7 plus 3, or x equals 10. On the negative side, we get x minus 3 equals -7. Moving that 3 to the other side again, we would get x minus 3 plus 3 equals -7 plus 3. This would give us x equals -4. If we were to graph this line, it would look something like this. The absolute value of x minus 3 line shows us that when x equals -4, y equals 7, and when x equals 10, y equals 7. This is why the absolute value of x minus 3 will equal 7. 5. The absolute value of 8 minus 3s equals 9. Again, from our properties of absolute values, we know that the absolute value of x equals d if and only if either x equals minus d or x equals d. So in this case, we get 8 minus 3s equals 9, or 8 minus 3s equals -9. Starting with the positive side, we start with 8 minus 3s equals 9. Let's move the 8 to the other side such that we'd get 8 minus 3s minus 8 equals 9 minus 8. This would leave us with minus 3s equals 1. Dividing the -3 by both sides, we would get s equals -1/3. On the negative side, we have 8 minus 3s equals -9. Moving the 8 to the other side again, we would get 8 minus 3s minus 8 equals -9 minus 8. This would leave us with minus 3s equals -17. Divide both sides by -3, and we get s equals 17/3. Number 6. The absolute value of 3x minus 7 is less than 2. From our properties of absolute values, we know that the absolute value of x minus a is less than d if and only if a minus d is less than x, which is less than a plus d. Rearranging then, we would get minus 2 is less than 3x minus 7 less than 2. Moving the 7, which is the a, to the other side, we would get minus 2 plus 7 is less than 3x, which is less than 2 plus 7. This would give us 5 is less than 3x, which is less than 9. Divide everything by 3, and we would get 5/3 is less than 3x over 3, which is less than 9/3. This would give us 5/3 is less than x, which is less than 3. So we can write parentheses 5/3, comma 3 end parentheses, or 5/3 is less than x, which is less than 3. Number 7. The absolute value of x minus 3 is less than 2 times the absolute value of x. Turning to our properties, we know that the absolute value of x minus a is less than d if and only if a minus d is less than x, which is less than a plus d. So we can use this to say that the absolute value of x minus 3 is less than 2x, if and only if 3 minus 2x is less than x, which is less than 3 plus 2x. Alternatively, we also have the situation where the absolute value of x is greater than d, if and only if either x is less than minus d or x is greater than d. In our case, we would have the absolute value of x is greater than x minus 3 over 2, if and only if x is less than negative x minus 3 over 2, or x is greater than x minus 3 over 2. Working with the absolute value of x minus a first, we'd get the situation where we have 3 minus 2x is less than x, which is less than 3 plus 2x. Let's split this up into the two parts. The left-hand side would give us 3 minus 2x is less than x. Moving the 2x to the other side, we'd get 3 minus 2x plus 2x is less than x plus 2x. This gives us 3 is less than 3x. Divide both sides by 3 and we get 3 divided by 3 is less than 3x divided by 3, or 1 is less than x. The right-hand side of this equation would give us x is less than 3 plus 2x. Removing the 2x again, we would get x minus 2x is less than 3 plus 2x minus 2x, leaving us with minus x is less than 3. If we times both sides by negative 1, we'd get x times negative 1 is less than 3 times negative 1. Overall, we get x is greater than negative 3. Starting on the other equation, in the negative section, we would get 2x is less than negative x minus 3. Distributing that negative, we would get 2x is less than negative x plus 3. Moving the x to the other side, we'd get 2x plus x is less than negative x plus 3 plus x. This would give us 3x is less than 3. Divide both sides by 3 and we'd get x is less than 1. On the positive side, we get 2x is less than x minus 3. There's nothing to distribute here, so we'd still get the 2x is less than x minus 3. Moving the x to the other side, we'd get 2x minus x is less than x minus 3 minus x. Altogether, we'd get x is less than minus 3. We can see that there seems to be a contradiction. If we put these together, we could see that this would say negative 3 is less than 1, which is less than x. We could have a stronger case than just saying that 1 is less than x. If we put these together, we would get x is less than minus 3, which is less than 1. So it would be a stronger case to say that x is less than minus 3. So let's draw the absolute value of x minus 3 and 2 times the absolute value of x. From a different question, we have already seen what the absolute value of x minus 3 looks like, and it looks something like this. The line 2 times the absolute value of x would look like this. If we were to shade in the areas where the absolute value of x minus 3 is in fact less than 2 times the absolute value of x, we would shade in these areas here. We can see then that the answers that we found were actually a description of the picture, where in some cases the absolute value of x minus 3 is going to be greater than 2 times the absolute value of x. And in different parts of the graph, the absolute value of x minus 3 is going to be less than 2 times the absolute value of x. So then we can see from this picture which of the answers we want. We can see then that when x is less than minus 3, the absolute value of x minus 3 is less than 2 times the absolute value of x. And when x is greater than 1, the absolute value of x minus 3 is less than 2 times the absolute value of x. This means that we would write the set that we are looking for as negative infinity to minus 3 union 1 to infinity. Number 8. Show that the absolute value of a minus b is greater than or equal to the absolute value of a minus the absolute value of b holds for all real numbers. Let's first assume that we know that all of the numbers are going to be positive. When doing so, we can say that the absolute value of a minus b would be equal to the square root of a minus b squared. Expanding, it would equal the absolute value of a squared minus 2 times a times b plus b squared. We can do the same for the other side, such that the absolute value of a minus the absolute value of b would give us the square root of the absolute value of a minus the absolute value of b all squared. This would equal the square root of the absolute value of a squared minus 2 times the absolute value of a times the absolute value of b plus the absolute value of b squared. Note in this case then that the absolute value of a squared would equal the square root of a squared squared, which would equal plus or minus a squared, which would equal a squared. Therefore, we could write that this would equal the square root of a squared minus 2 times the absolute value of a times the absolute value of b plus b squared. Putting these back together, we would get the square root of a squared minus 2 times a times b plus b squared is greater than or equal to the square root a squared minus 2 times the absolute value of a times the absolute value of b plus b squared. Square both sides to get rid of the square roots, and you just get a squared minus 2ab plus b squared is greater than or equal to a squared minus 2 times the absolute value of a times b plus b squared. Getting rid of the a squared and the b squared from both sides, we would just be left with minus 2 times a times b is greater than or equal to minus 2 times the absolute value of a times b. Divide both sides by negative 2, and we would get that a times b is less than or equal to the absolute value of a times b. Since the absolute value of a times b will always be a positive number, the a times b side can be negative. And so we can break this up into a few cases. If a is less than b, then we could have three possible cases. A is greater than 0 and b is greater than 0, meaning both numbers are positive. Or a is less than 0 and b is greater than 0, meaning a is a negative and b is a positive. Or a is less than 0 and b is less than 0, meaning both numbers are negative. This would give us the three cases of positive a times positive b is less than or equal to the absolute value of a times b. And this would give us that a times b is less than or equal to a times b. The second case, negative a times positive b is less than or equal to the absolute value of a times b. This would give us negative ab is less than or equal to ab. The third case, negative a times negative b is less than or equal to the absolute value of a times b, which would give us a times b is less than or equal to a times b. We can also examine one more case, where if b is less than a, implying that a is greater than 0 and b is less than 0, meaning a is positive and b is a negative. This would give us positive a times negative b is less than or equal to the absolute value of a times b, which would again give us negative ab is less than or equal to ab. So, a times b is less than or equal to the absolute value of a times b holds true for all real numbers. Therefore, the absolute value of a minus b greater than or equal to the absolute value of the absolute value of a minus the absolute value of b also holds true for all real numbers. And that will conclude Calculus Lesson 1. More calculus lessons, as well as chemistry and physics lessons, will also be coming to the channel, so don't forget to subscribe, like the video if you enjoyed it, leave any comments or questions down below, and I'll see you in the next video.